This is your homework corrections for section 7.1.5, starting with problem 770. So they want you to use the fraction buster technique to solve these problems. Remember, the idea of the fraction buster technique is to look at the denominators of the fractions, think about what is the least common denominator or least common multiple of the denominators, and multiply the terms each by that. So what you end up doing in this case is looking at the 2, 5, and 10 and realizing that the common denominator or least common denominator is 10. So we're going to multiply everything by 10. When we do that, when we multiply this by 10, this term here, the 2 and the 10 are going to simplify. 2 divided by 2 is 1. 10 divided by 2 is 5. So we're going to have 5 times 3, or 15. When we multiply this term by 10, the 10 and 5 are going to simplify. 5 divided by 5 is 1. 10 divided by 5 is 2. And 2 times 2x is 4x. And we multiply this term by 10. The 10s are going to simplify. 10 divided by 10 is 1. 10 divided by 10 is 1. 1 times 7 is just 7. So what you're creating is an equation now that does not have any fractions in it. That's why we call it the fraction buster technique. Then you're going to solve this as you normally would. We want the variable by itself on one side, the constant by itself on the other side. So we're going to subtract 15 from both sides. This is going to zero out. We're going to get 4x equals negative 8. And then we're going to divide by 4 on both sides. X equals negative 2. It does not say that you need to do a check, so you don't. For the fraction buster technique on this one, we're going to look at the denominators of 5, 6, and 3 and realize that the least common denominator or least common multiple of the denominators is 30. So each of these terms are going to be multiplied by 30. We take the first term and multiply by 30. The 5 and 30 are going to simplify. 5 divided by 5 is 1. 30 divided by 5 is 6. 6 times negative 8x would give us negative 48x. We're going to multiply this term by 30. Again, the 30 and the 6 will simplify. 6 divided by 6 is 1. 30 divided by 6 is 5. 5 times 1 is 5. And we're going to multiply this term by 30. 30 and 3 will both simplify. 3 divided by 3 is 1. 30 divided by 3 is 10. And 10 times negative 5x is negative 50x. So we end up getting negative 48x, 6 times negative 8x, plus 5, 5 times 1, equals negative 50x, negative 5x times 10. Again, our goal is to get the variable on one side, the constant on the other. So we already have the 5 by itself. There's no constant term on this side, is what I mean. So we'll leave that be, and we're going to want to shift that negative 48x. So we're going to add 48x to both sides. The reason I point that out is sometimes people would say, well, why don't I add 50x to both sides? And mathematically, that's not wrong, but again, it's not going to get us what we want, which is the constant term by itself on one side, the variable term by itself on the other. So we are going to simplify this, and we get 5 equals negative 2x when you combine these. Again, we don't want the value of negative 2x, we want the value of just x, so we're going to divide both sides by negative 2, the coefficient on the x. This creates the 1, so 1x, and 5 divided by negative 2 is negative 2.5, or negative 2 5/10. For 771, we want to find the value that makes the equation true of x in each case. So here we basically are set up for a one-step equation. We just divide both sides by negative 4 9/10. X equals negative 2, because that's what 9 8/10 divided by negative 4 9/10 is. Here, we would probably want to look at a different way of doing it. There's a couple different ways we could approach it. One is we could simply divide by the coefficient on x, which is the fraction. because this again creates a giant 1. And then you can put into your fractional scientific calculator 8 over 21 divided by negative 2/7. You also could have approached this with a fraction buster technique as well. Either way, you end up getting an answer of negative 4/3 for x, which is the same as negative 1 1/3. And here, we'd subtract 3/5 from both sides. Again, you're allowed to use a scientific calculator. You get x equal to 1/15. Again, it does not say we have to check, so we don't. 772. Trina planted 43 plants in her garden last week. She planted twice as many cucumbers as zucchini and 8 more tomatoes than cucumbers. We have to write and solve an equation that finds the number of each kind of plant in her garden. And if you want to, you can use the 5D process to help you organize your thinking. You do need to define your variable. So what we know is she planted twice as many cucumbers as zucchini and 8 more tomatoes than cucumbers. So we're going to start with letting x be the amount of zucchini that was planted. Okay, she planted twice as many cucumbers as zucchini, so the number of cucumbers would be 2x. And she planted 8 more tomatoes than cucumbers. Cucumbers is 2x, so tomatoes would be 2x plus 8. And then we are going to say that if we add up the number of zucchini and the number of cucumbers and the number of tomatoes, that's going to equal the total number of plants, which is 43. So x plus 2x plus 2x plus 8 equals 43. So again, you would combine your like terms first. X plus 2x plus 2x is 5x plus 8 equals 43. Subtract 8 from both sides. 5x equals 35. Divide both sides by 5. And x equals 7. Again, that's how many zucchini she planted, but they want us to find the number of each kind of plant in her garden. So if there were 7 zucchini, then the number of cucumbers would be 2 times 7, or 14. And the number of tomatoes would be 2 times 7 plus 8, or 22 tomato plants. For 773, you need to complete the scaling. In other words, put in the missing values. So what we see is we have 0 here and 60 here, and we have 3 spaces in between. So that means difference between them is 60 divided by 3. We're going up by 20s. So we'd have 20, then 40 is missing, 60 was given, 80 is the other missing value. For B, we have a difference between 0 and 60 of 60, but now we have 4 spaces. 60 divided by 4 means we're going up by 15. So 15, then 30, 45. Again, 60 was given, but 75 would be missing as well. Here we have 0 to 100, so a difference of 100, and there's 4 spaces. So we're going by 25. So 25, 50, 75. Again, 100 was given, but 125 is also missing. And here the difference between 0 and 100 is 100. There are 2 spaces, so we're going by 50s. 50, 100 was given, 150, 200, 250. For 774, Mount Rose Middle School collected canned food to donate to a local charity. Each classroom kept track of how many cans it collected. The number of cans in each room were this, and the principal displayed the data in this box plot. So first of all, just to remind you of what a box plot shows, this is the lowest value, this is the highest value. The value here is the median. The value here is, we call it Q1 or quartile 1, meaning halfway between the lowest value and the median. The value here is Q3 or quartile 3, halfway between the median and the endpoint. So again, if you think about this as like the idea of a football game, this is like the first quarter. All these values are in the first quarter. Here's our end of the quarter, Q1. The values here would be between first quarter and the half. the values here between half and third quarter. So this is our Q3 into the third quarter. And the values here are in the fourth quarter. So these are all 25% of the data. 25% of the data is between 39 and 62. 25% is between 62 and 73 and a half. 25% is between 73 and a half and 80. And 25% is between 80 and 107. So the interquartile range is always found by taking the value for Q3 and subtracting the value for Q1. In other words, the ends of the boxes get subtracted. So 80 minus 62 gives you 18. Now what they want you to do is to recognize that we can add additional information and we can make a new box plot. So if the main office staff collected 55 cans, the counseling staff collected 89 cans, and the custodial staff collected 67 cans, they want us to make a new box plot. Again, clearly label the median and first and third quartiles. So what we would now have is taking the data they already gave us, adding this additional data, we would need to put it in order from least to greatest. So what I've done is taken these values, added these values, and then put them in order from least to greatest. We're going to start by finding the median. So again, the median is the middle value when the numbers are in order. So that'd be 70. Okay. Then when the median is a number right in the middle here, 70, we're now going to look at the first quartile as being the values up to 70 and the third quartile being halfway between the values after 70. So we want to find the median of the first half of the data. So 39 and 67, 55 and 65. The first quartile is between 55 and 62. So what is halfway between 55 and 62, you might ask? Again, you have the access to a calculator, so you can add them up and divide by 2. So 58 and a half, 58.5 would be the first quartile. So 58.5 is Q1. Then we're going to find the value that's half of the second half of the data. In other words, the median of the second half of the data. So again, work our way to the middle. It's between 80 and 86. Probably do that in our head. Halfway between 80 and 86 is just 83. So that's our Q3. Then what we're going to do is we're going to make our box plot. Okay, so you start by putting your values. You have a line below, and you should go by even increments. So they went by tens. You don't have to go by tens, but you certainly can. You could also have gone by fives. You wouldn't want to go by ones. It's just too many numbers you'd have to put on there. And then what you want to do is you want to start by finding where the median is, which is 70, and putting a line there. So we're going to put a line at 70 because that's the median. Then we're going to find approximately where the first quartile is, 58 and a half. Again, it's going to be an approximation. It's about here between 50 and 60. So we're going to put a vertical line, and don't forget to mark that value, 58 and a half. Then we'll find the value for Q3, 83. Again, you're approximating. Mark that, and don't forget to indicate the value. And then we connect these to create our box. So this is quartile 1, median, quartile 3, connect and create your box. Then we always do what they sometimes call a whisker. So sometimes this is called a box plot, sometimes it's called a box and whisker plot. But the idea is that you're going to make a line to your lowest value. Your lowest value is 39. I oftentimes find it's helpful to also mark that up here. All right, and then you're going to make a whisker on the other end to your highest value on your list, which was 107. So again, I would probably mark that as well. So what we're saying is A fourth of the data in this list is between 39 and 58 and a half. A fourth is between 58 and a half and 70. A fourth is between 70 and 83. And a fourth is between 83 and 107. So what a box plot does, or again sometimes called a box and whisker plot, is divides it into fourths. It's a way of analyzing data in a more thorough manner. For 775, they want you to take this data and start by making a stem and leaf plot. So remember that your stem and leaf plot should have a title, so the ages of the golfers, should have your stem. In this case, when you look at the value, these are all 2-digit numbers, so it makes sense to have our stems be the tens digit and the leaves will be the ones digit. And so we have these values. So this is representing the golfer that's 25 years old. This is representing the golfer that's 28 years old. This is representing the golfer that's 29 years old. Okay. We have two golfers that are 34 here and here. So that's why we have the 4 listed twice. So remember, with the stem and leaf plot, you should have some type of key or legend like this. 2 with a stem of, a stem of 2, a line, and a leaf of 5 means 25. You can use any value here. You could also say this means 25 years old, if that is more complete. And then when you do your stem and leaf plot, remember you need to have all of your values from where you start to where you end up, so 2 to 7, even if they don't happen to have any leaves. So for example, if there was nothing in the 60s, you would still represent the 6 in your stem and leaf plot. And then also don't forget that these values need to be in order from least to greatest. Then you take that stem and leaf plot and they want you to make a histogram from that. When you make your histogram, again, you need a title and you need labels. And your label for your vertical, remember, is always going to be the frequency. And what we find is that there's 3 golfers that their age is between 20 and 30. So height there is 3. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 golfers whose age is between 30 and 40. Remember, if something lands directly on a spot, like there's a golfer who's 30, that's going to be in the 30 to 40 section, just like it's in the 30 to 40 section over here in the stem and leaf plot. So you're going to take this information and create this histogram. Then they want you to describe the shape and the spread. So the shape of the spread have to do with, is there symmetry or not? Is it single peaked? Is it double peaked? Is the data very spread out? So what they say is it's mostly non-symmetrical. Remember, again, the idea of symmetry is if we would visualize a vertical line coming through, are both halves pretty much mirror images of each other? And the answer is they're not. They're not very much mirror images of each other. So that's why they say slightly non-symmetric. And certainly it has a single peak, one highest bar compared to the others. And then is there any outliers? Well, if you look at this information, especially in the stem and leaf plot, 74 is quite a bit larger than the other golfers' ages. The highest one up to that point is 61. So 74 could be considered a possible outlier, meaning it's a little bit larger, or an outlier could be smaller than the other values. And then they want you to describe a typical age. Well, a typical age, remember, is always a median or a mean. The median, if you put these numbers in order and pick it out, is 43. And again, if there is outliers, we usually say median is a better choice because the mean can be skewed by outliers. But actually, if you figure out the mean, it's not too far off either, because there were some lower ages of golfers that also sort of averaged this out.